Welcome to a lesson with Dr. Powell. Let's take a look at how arc length is computed in polar coordinates. Let's consider the setup. So, as we move from one point to another, so the curve here goes from here to here, maybe a little curved in some way or another. Notice that, suppose this is the origin, and we have a line here and a line here, and a line here. And suppose that R has increased. So let's kind of draw a sector here, kind of around the center where this would be R, but R has changed. It's grown by a change of dr. Theta is also changed, and it's represented right here, d theta. Now the arc length right here is r d theta. Let's look at that picture right there up close. So we have kind of a circular arc thing. We're going up, and actually on the tangent, this is perpendicular, on the tangent that is. And then we have something that's curved that goes like this, down to this point. This is dr, this is r d theta. Now, as d theta gets smaller, this circle right here looks more and more like its tangent line. So it looks more straight, more like a tangent line. Also, assuming that this has nice derivatives, it's going to look like its tangent line too. It's going to be a straight line. So it's actually, eventually, in a limit, things limit to look like a right triangle. And these symbols themselves are limit type symbols. So this is perfectly valid. So the relationship between them is the same as what would happen in a limit, which is a right triangle and a Pythagorean theorem. So the little change in arc length right here can be written differentially right here. Using the Pythagorean theorem, the square root of dr squared quantity plus r d theta quantity squared. Now we can rewrite this by factoring out the d theta squared. So we have d theta squared, and that lives with r squared, and over here, dr over d theta quantity squared. Thinking of these differential lengths in this sense as being actual lengths, and their ratio here in the relationship, how they're related in the picture, is going to be the derivative, dr over d theta, because we're looking tangentially at a point where these symbols only exist right there at that point, and their relationship, their ratio is constant, and it is the derivative dr over d theta. So this is valid, and we can, in taking a square root, we get d theta, and then we're left with, here underneath the square root, dr d theta squared plus r squared. And so this right here is a little piece of arc length. Now, if we integrate that, dr d theta squared plus r squared d theta, as our theta value goes from something to something else, this will actually yield arc length of a polar curve. This derivation is intuitive. I didn't use rigorous results. Nonetheless, the ideas are valid, and they can be made rigorous. Thanks for watching.